Alright, so welcome to this very video. In this very video, we want to look at some past questions on physics, and today we'll be looking at physics 20, the past question on for 2019. Now, before you can be able to solve physics past question, you must be able to do some things. Now, the first thing is you must be able to read. I should believe that you can't be studying physics without being able to read. The next thing is that you must be able to interpret question, understand the question, so that you can be able to detect some of the things you are given. You know, sometimes a physics question will tell you the mass of the body is 10 grams or 10 kilograms. Then you have to, sometimes they won't tell you, they will say a body of mass 10 kilograms. You must be able to know that what anything gram or kilogram measures mass. So you must be able to understand that in trying to interpret that very question. And then also you also need to know how to write out your parameters. That is a key step in solving physics problem. Now you must be able to write out your parameters. And what do I mean by that? Writing out all the quantities that you have been given, and from there you see what the quantities that you are asked to find. Then, and what's the next step? The next step is what you look for a suitable equation that can suit your question. Now sometimes you are given multiple questions, you don't know where the topic topic comes from, but when you have the knowledge of you can be able to understand or to interpret question, you will know that quickly this topic is from mechanics, or it is from thermodynamics, or it's from anywhere. So that is just the best way for you to be able to solve physics problem. Now going back to what we have today, like another thing you need to know, you also need to know how to manipulate your way into solving a problem. What I mean by this, sometimes in mathematics and also generally in science, you could be given a question, but that question, before you are able to answer that question, you need to answer a lot of other questions. So you must be able to see the way you can be able to solve problem from so many you pass through so many steps before you can get your final solution. So that is why you have to possess those skills, understand the question. So we are going into the video what we have for today. But don't forget to subscribe, hit that subscribe button. I'll be back. Alright, the first question says a body of mass 20 grams is released from a catapult whose rubber is stretched through 5 centimeters. So let us write out that parameter. We have a body of mass 20 grams is released from a catapult whose rubber is stretched through 5 centimeters. So the rubber is stretched. It is stretched. That's the extension is what? 5 centimeters. Now, if the force constant of the rubber is 200 Newton per meter, so the force constant K is what? 200 Newton per meter. Now calculate the speed with which the stone leaves the catapult. So we have to calculate the speed with which we are looking for the speed V with which the stone leaves the catapult. You know, when you pull a catapult, what you are going to be storing in that very catapult is what? Is potential energy. Now the minute you release that very stone, whether it is a stone or whatever, the next thing is that what that very potential energy is converted to kinetic energy. So, and that kinetic energy depends on what? The velocity. So the maximum potential energy that you are given to it will give the very stone an initial what? Maximum velocity. So let's really look at what that is. So looking at this everything we have here, we discover that what? That this problem is what? Is based on elasticity and Hooke's law. Now Hooke's law clearly states that what? That force is what? Is proportional to what? To the extension, provided there's a constant. This constant, we call it what? The force constant of the elastic material. Now let us but you know Newton Newton and meter here, they are the SI units, right? So this one is what? CGS units. You have to convert units. That is another thing you need to know how to do in physics. You have to be able to do what? To convert from one unit to another. Now you have to convert gram to kilogram is by dividing by what? By 1000, so that we get what? 0.02 kg. Then this one 5 centimeter, we divide it by 100, we get what? 0.05 meters. Now if the velocity of the it is the velocity we want to get now. Now what is the potential energy that is stored in an elastic material? That potential energy, PE, equals what? K half KE square, right? Now, and this potential energy is going to be converted to what? To kinetic energy of the stone when it leaves. So that's going to be what? And what is kinetic energy? It's not half mv square, right? So we can make v subject of the formula from here. So we are equating this. So the maximum potential energy is converted to what? Let's just put this over 2. The maximum potential energy is converted to what? To kinetic energy, and this velocity is what we are looking for. So let us equate these two. We have what? V square equals what? Let's do it this way so that everybody can understand very well. Half mv square equals what? K E square over 2. Now I'm going to multiply both sides by 2. 2 cancels, 2 cancels. So I have it at what? Mv square equals what? Ke square. Now I'm going to divide by m, then so this is what we have. We now have that what? V square equals what? Ke square over what? Over m, right? So that V is what now? Take the square root of both sides, so that we have what? Root of k over what? M, then times what? E. So let's punch this. This is what we are going to punch. I can bring this one to the back here. The extension is 0.05 times root of the first constant is 200 over what? The mass is what? 0.02. So we are going to punch this in our calculator and see what we'll get. 0.05 times square root of 200 over 0.02, and this we get 5 meter per second. So the velocity here is what? Is 5 meter per second. So that's the first question solved. Now let's move on to the next question. The next question says we have an image here. So we have this. Alright, this very question tells us to define the terms P, beta, H, and then R. Now, what is P? This is describing projectile motion, right? This diagram here describes a projectile motion. Now, when you throw a body at a certain height, let's say I choose this height to be the height with which I want to throw the body in a parabolic path, so that it's going to travel through a parabolic path. That's projectile motion. Now, that velocity, the initial velocity that it leaves, or that I throw it, that initial velocity is called what? Is this very P here. So that's the initial velocity, and that very velocity is going to have what? The vertical and what? And horizontal component. Then this angle beta is what? Is the angle of inclination of what? Of the horizontal velocity with the what? With the velocity itself, P, and what? And the horizontal line, on this horizontal line. Then H here is what? Is the maximum height that is the maximum height that the what, that the very stone or whatever is thrown can get to. Then r here is what? R is the range, and this range measures the horizontal distance traveled. That is, this horizontal distance traveled is what? Is the distance, horizontal distance covered, during which the stone returns what? To the level or the height that it was what? Initially projected. So that is what? That is r here, and that is that. Now you must know that what? This very velocity, like I said, it has two components. It has the y component and what? And the x component. Let me just use this opportunity to say something about projectile motion. You must know that what? Projectile motion, the way it is that if you project a body with an initial velocity p, which is at an angle to the horizontal, now the vertical component of this very velocity is going to be what? Let's call it py. It's going to be what? P sine theta, and the horizontal component px is going to be what? P cos theta. Or sorry, we are using beta in this case. We are using beta here. Let's make it beta. Now, what does what happens to the velocity as the body leaves this initial position? Now, when the body is going upward, we must know that what? That the velocity is going to change. It's no longer going to be p. So what happens is that what component is going to be responsible for the change? That's the next thing. It is what? It is only the vertical component, and that is because of what? Because of acceleration due to gravity. You know, gravity is pulling that very object that is being thrown upward in a parabolic path. Gravity is pulling it down. If not, it should continue with this velocity like that. So because gravity is pulling it down, the very stone will do what? Will do what? Will be reducing its velocity as it is traveling upward and upward. Now it gets to a particular height where the vertical component of the velocity now becomes what? 0, and that's where we have what? The maximum height. Then that means as it begins to fall again, you know, acceleration due to gravity acts downward. That means that what? That the very stone begins to gain vertical component of velocity again, and it increase until it returns to the same velocity p that it was initially thrown. Now, but what about the x component of the velocity? The x component of the velocity does not change, and the reason is that what? Acceleration due to gravity does not affect the horizontal component, so it acts downward. So when things act perpendicular to each other, it can't be affected by that. So that is why the horizontal component of the velocity remain constant, and this is so said if air resistance is neglected, and any other physical force or agency that could cause the body to change velocity. So the horizontal component should remain constant. Let's look at the second part of that question. Now, is it write an equation to show the relationship between P, G, and R, where G is what? And R max. R max. Now, R max there is what? Is the maximum range or the maximum horizontal distance that the body can travel. So we have to find the relationship between P. We are just to write P. We have P. We have R max. Then we have what? We have G. Now it happens that what? It is P R max that is going to be in terms of what? P and G. So R max is going to be what? P square G. P square over what? Over G. Now when do we have R max? We have R max when the angle between the angle of this very inclination of what? Of the velocity with the horizontal is what? Is 45. And let's see how that is so. This is so because we have that R max, normally the range should be what? The range should be p square sine 2 theta over what? Over g. So when theta here is 45, so it's going to be what? Or we are using beta. We know we are always used to. Let's use beta. 2 beta. Now when beta is 45, then this thing becomes what? 90, right? 2 beta becomes 90, and sine 90 is 1, and then you go back to this. So this is the equation that relates what? R max and the horizontal velocity. Now I'm going to make a video especially on this very projectile, so that you can be able to understand projectile very well. We'll solve a lot of questions on it, and then if you come out from that video, you can't be afraid of any projectile question. Let's move on to the next question.
Now the next question says, state 3 observable phenomena in which waves behave as particles. Now we want to look at some of the properties that make us say that wave has a particle nature. So let us look at it now. Number 1, we are going to be talking about black body radiation. Now, black body radiation is the radiation or the thermal electromagnetic radiation that is usually around a body that is in what? That is in thermodynamic equilibrium with its environment. So if we want to talk about what thermodynamic equilibrium is, it's going to be a long thing, but for us to just understand, a body is said to be thermodynamic equilibrium with its environment if it maintains the same temperature, it maintains the same chemical composition, it also maintains the same mechanical energy or pressure during that specified time. Now you must understand that black body radiation takes place only with black bodies. That is, that black body is going to be a non-reflective body. It's an ideal body. It does not reflect light, or it does not reflect any ray that is incident on it. You might ask that if these black body radiations really exist, why can't I see it in dark places? The reason is because the radiation that is usually around these bodies is beyond is beyond the visible spectrum of light. This is the infrared spectrum, and so it cannot be seen even if this very radiation is in the dark. Now let's go to the second thing we have to talk about. We want to talk about photoelectric effect. That's another proof that wave behaves like particle. What is photoelectric effect? Photoelectric effect is a phenomenon that is used to describe the emission of particles from the surface of a material when they are hit by light or other electromagnetic waves. So when the surface of a material is hit by light rays, they emit electrons. That is what photoelectric effect is. One of the ways in which you can be able to detect the wave and particle duality of light. So that is one of the proof. Number 3 now is the Compton effect. Now, Compton effect was discovered by US physicist Arthur Compton. He discovered that when high energy photons or other electromagnetic waves are scattered by electrons, their energy is reduced, and correspondingly their wavelength increase, and while the energy of the electrons are increased. So this is what we call Compton effect. It's another way of proving that what? That wave has what? Nature of what? Of particle. Do not also forget other wave properties such as reflection, refraction, diffraction, polarization, and interference. They are also one way you can be able to determine or detect that wave is a particle or has particle behavior. Look at the question says, state three magnetic elements that determines the Earth's magnetic field at a point. Now, you must be able to understand the fact that the Earth behaves as if it has an imaginary bar magnet in the center, that is in the core. Now, this very magnetic field of the Earth, which is also called geomagnetic field, has to do with the fact that there is convection current right from the core of what? Of the Earth, that is the center of the Earth, due to the temperature difference and some other things like that. So this Earth behaves as if it were a magnetic field, and so for us to be able to determine the magnetic field at any point on the Earth, we talk about what? The magnetic field, the Earth magnetic field elements. What are the Earth magnetic field elements? We'll look at them now. Now, you must understand the fact that for magnetic field to occur, there must be what we call current. There must be current flow. That is why, as there's convection current right from the core of the Earth. The Earth behaves as what? As if it has a bar magnet right in its center. Now let's look at how to determine the magnetism now. These three components are the angle of dip or inclination. Number 2, the angle of declination or variation. And number 3 is the horizontal component of the Earth magnetic field. Really, what are Earth magnetic field elements? They are simply elements that determines the magnetic field of the Earth at a particular point. Now let's consider them one by one. The first one is angle of dip. So what is angle of dip? To understand this very well, let's look at this very image closely. The image we have here shows us that the geographic north is not in the same direction as what? As the magnetic north of the Earth's magnetic field. And so also the magnetic south is in the northern direction of what? Of the geographic north of what? Of the Earth. Now, this shows that and you can also see that what? That the lines of the magnetic field is not exactly parallel to what? To the magnetic or to the geographic meridian. That is, the magnetic meridian is not parallel to what? To the geographic meridian. Now, the two lines I'm talking about, which are the magnetic meridian and the geographic meridian, are these. So here we see that there is an angle between the geographic meridian and the magnetic meridian. Now, remember that one way to determine the magnetic field of the Earth at a point is by suspending a bar magnet in space, and the direction of the magnet will show the direction of the field at the direction of the magnetic field at that very point. The vertical line that passes through the magnetic axis of a freely suspended magnet is that thing we call the magnetic meridian. But the geometric meridian is just the line, the vertical line that runs from what? From the north to the south of the earth. As simple as that. Now let's go back to the angle of dip. Now, the angle of dip is simply the angle between the horizontal on the earth and the resultant direction of what? Of magnetic field. So if you draw an horizontal line on the earth now and then you suspend magnet, the angle of inclination of that very magnet with respect to the horizontal is the angle of what? Inclination. Let's go to the second one now, which is angle of declination. Now for us to understand that, we have to look at this very image again. Now look at the magnetic meridian and the geographic meridian. You can see that there is an angle between them. That is just what we call what? The angle of declination. So the angle of declination is the angle between the geographic meridian and the magnetic meridian. Another element that we need to describe the Earth's magnetic field at a point is the horizontal component of the field at that very point. Now, if we resolve the resultant magnetic field, we will get the vertical and horizontal component, and we are now interested in what? In the horizontal component, which can also help us to determine the magnetic field at that point. So that's it.